Quantum mechanics tells us that objects can behave like both waves and particles, and they can even be in a superposition of two places at once. Experiments have confirmed this counterintuitive behavior for systems ranging from electrons to atoms, molecules, and even large molecular footballs. All of these objects, though, are still microscopic, leaving the obvious question: can we make a superposition of something bigger? Can we, for example, make a drum that vibrates and stands still at the same time? Quantum optomechanics can tackle this question, where light is used as a drumstick to play a quantum drum. When a particle of light, a photon, reflects from the drum, it gives the drum a small momentum kick, and concurrently, the drum's position changes the phase of the reflected light field. As the kick of a single photon is very small, it is very difficult to observe this small momentum change above the mechanical thermal fluctuations. For this reason, generating a quantum superposition of mechanical motion remains a highly sought yet outstanding goal in the field.
We propose a new approach to generating mechanical quantum superposition states by using the quantum nature of light and photon counting measurements, partly inspired by photonic quantum computing. In our experiment, a very weak laser beam is sent into an interferometer where one arm reflects off a mirror while the other arm reflects off a vibrating drum. In our case, the drum is a millimeter scale silicon nitride membrane which is visible to the naked eye. The two beams of light are then recombined to interfere, and we count how many photons are in each output. A key aspect of our approach is whenever we observe exactly two photons, one in each output port, we know that due to the Honger-Mandel effect, the only way this can happen is if we had an entangled state inside the interferometer. This state is two photons on one side and zero on the other, or vice versa. This means the membrane receives a quantum superposition of nothing and a two-photon kick. So if the membrane was standing still in the beginning of the experiment, it would now be vibrating and standing still at the same time. We performed a proof-of-principle experiment with a membrane at room temperature, which is not cold enough to see mechanical non-classicality. However, the setup was sufficient to perform the first observation of mechanical interference fringes in the membrane position, albeit with mechanical thermal noise. We studied this signature in two regimes. Firstly, when a photon kick is weak, our method would produce a single phonon Fock state, which in our high temperature regime still keeps the interference fringes in X but not in P. When the optical phase shift is large, on the other hand, we can see multiple fringes and we can make more interesting states. For example, our method could produce Schrödinger cat states of increasing size or even quantum compass states by changing only the optical measurement. Our proposal has a number of advantages. There is no need for strong single photon coupling. It is more robust to non-zero temperatures of the mechanical resonator, it is loss resilient, and the scheme is very flexible, since making different states only requires changing the optical measurements. The next generation of these experiments may reveal new intricacies of quantum mechanics, including decoherence and non-classicality, and may even help light the path to a theory of quantum gravity.